let's talk about regressions. Regression is, you will say, this is probably the first topic in machine learning. And so far, it's linear algebra and optimization is kind of prerequisite that I believe that's a mathematical background that we need for better understanding of machine learning. Actually, this is the first moment that we talk about the machine learning. The first topic is going to be regressions. And for regressions, we have regression 1 and regression 2 and regression 3. Actually, 3 different topics that we have. So we're going to spend quite a time for the regressions. So let's jump into. Let's start with simplest case. Suppose you have. Suppose you have X and Y, and think X as input and Y is as output. And how do I say you conduct some of the experiments or simulations, and if you give the X as inputs, the experiment outcome probably, like your measurement, is going to be in the Y. And say how many experiments that you conducted? 13 times. You have 13 data points. And probably assume that you conduct some kind of experiment. It doesn't, any kind of experiment. And probably you created like this table, because you did 13 times, you will get some values, write it down, or use some Excel files to record it. This is the data points that you have. Right? Some, like, imagine in the Excel file, you have 2 columns and some values, like that, like pair of data points, 13 data points. And say by just looking at these tables, you have no idea, so you decide to plot it. And this is the plot. And you might think that's some kind of relationship between X and Y, kind of relationships. And you decide to have some kind of models to represent the relationship between an input and outputs. You decide to create, you decide to build, you decide to construct some kind of models. You want to have some kind of functions that X as input and Y as output. Right? In general, say Y is, I mean, probably some approximations on f of X. Right? And let's think about the simplest function that you can have. The simplest functions. What will be the simplest functions for f? Linear models. That's the simplest model. So I mean, you know that y is ax plus b is right. So let me see. In many cases, linear model is used to predict y. I would say y is measured and y hat is predicted values out of. So here, let me change the notations like that. Y hat X is ith values, and ith predictive values is that some kind of, let me see, like zeros. That's your model. It's a linear model. and the X is input and Y is output, and theta naught and theta 1 is the parameters that you want to estimate it. And you might draw this kind of straight lines. I mean, given this point, there's nobody's gonna like say this is the fitting that you have. Probably not. And of course, this is not, or this is not. And most people like gonna try to draw the straight line like that. Corresponding slope and the y-intercept, and these are two parameters. So in plot or geometric meanings that to find the linear model is how do you draw the straight line like this. In the equations, the same thing, but in different way that I'm saying is that how do you find these two unknown parameters? That's the same action that you're trying to do. Because in two-dimensional space, I mean, this is the equations for that guy. So these are two equivalent expressions. One is how do you draw the straight lines, or the other one is how do you get the linear equations with the unknown parameters. So let me get back a formal definition of linear regressions. In general, input and outputs, we can have any functions of f, but in many cases, we assume that its model is linear. And we do have xi and xy, y of I as input and outputs. And suppose we have m data points. It could be like 100 or 1,000 or 1,000, like 1 million data points. It could be. And let me see. What is, I want to say y is different from y estimated. Estimated is like by 2 data points. Might be different. But what I'm trying to say, what I'm trying to hear is that I know these two values are different, but I want to the discrepancy between the measured data points, which is the actual values, and the predicted values from the linear models or out of linear regression model. I want to try to minimize them. I want to try to minimize the errors by having good numbers for theta naught and theta 1. So I guess you guys can guess this is now, I said I'm trying to get the best. That means this problem can be modeled as optimization problem. Or by looking at the figures here, okay, say we have, let me see, try this data point. We have here, and this one is the true values. But if this is the model, it's probably that one is predicted or estimated. The difference between these are the difference. all these we can think of as approximated errors. We can calculate it, that errors for all the data points. Right? And I want to minimize that. And like, think about it, like say, if that's the, you say you don't know the exact, you don't know the solutions yet. If you estimate it like that, probably these are errors between the true values and predicted values. If you compute and make summation for all of them, probably the total, the errors is huge. So it turns out it's going to be that this one is not the right answer for that. Okay. Okay, what I'm trying to say here is that I gave you the formal definition of linear regressions and conditions, and trying to reformulate it into the optimization problems. Which one is the decision variable in this problem? Right? There's two unknown parameters. Which one is the objective functions? Which one is the objective functions? Let me show you. Linear regression as optimization problem like that. And I put all the data points as a column vector. And this one is unknown parameters. And let me see, assume that the linear models and minimize, let me see, minimize measured data point, true. And this one is predicted out of these models. And squared, and take it for the entire data points, same as summations, and minimize it. This is optimization problem. The linear regression is optimization problem. I mean, then later on, okay, any given linear regression problems, we convert it like these optimization problems, and you don't have to solve it because you're gonna use a CBX pi to find out these unknown parameters or decision variables that are not and that are one. And once you know, estimate it, you can draw okay. And the purpose of having this model is that, say, suppose you have certain data points. And what if you have new observations as input? Say you say, I want to compute at this point, suppose you have unseen data points and as inputs. I want to know the best predictions that we can have with given certain data points is, sorry, this one is the best predictions that we can have. That's the only purpose that we want to build linear regression models. See, we have data points and build the models. Once we're done with that, new data points, I want to predict without doing actual experiment. So we can save the cost, save the money. Right, that's the kind of the entire pictures for regression models. So we can recast the problem as a least square problems. Let me show you. Let me see. Again, here I add 1 here. And then matrix and vector multiplications, and I did the transpose it. And suppose we have x as a x1, x2, xn, y is y1 and y2, yn. What you can do, x, right? And what I can do, y1, y2, yn, minimize, let me see, 1 x1, 1 x2, 1 xm, that are not, that are 1. So this is column vectors, and this will create another column vectors. So there's 2 vectors. I want to minimize the distance between them. So this column vector, same as in linear algebra that you're learning, is that ax, I mean, probably I will say a theta. What's the optimal solutions for that? You remember A transpose A inverse, things like that, like B. Remember that one? To find. So it turns out if you do this kind of trick, linear regression problem is least square problem, same as least squares. We can reformulate it like that. Like I hope that you guys are familiar with this, the least square problems, and this is the optimal solutions in just changing. Like here we have a and x, b. Here we have theta and y. This is column and column vectors in the matrix. That's why, that's the only reason that I introduced least squares in when you talk about the linear algebra, because we know that we're gonna use that for linear regressions. All right, so it's time up. Let me stop here, and I'm from next time I will start from here. So this is the moment that we're done with the linear algebra and optimizations, and now it start from the linear regressions. And while I explain the linear regressions, I'm gonna show you that how the linear algebra optimization can be utilized into the linear regression models. Right, to try to find that link and bridge between them is that's the key thing that I want you guys to see or study or understand. All right, so let me stop.